In this video, I'm going to show you how you can use a Raspberry Pi and an Arduino together. This is something I'm going to be using on future projects, but for now I'm just covering the aspect of getting the Raspberry Pi and Arduino to talk together. So why would you want to? Why not just use the Raspberry Pi or just an Arduino? In my previous video, Arduino versus Raspberry Pi, I compared the features of each, and one of the conclusions was that why settle for a compromise when you can get the best of both. Here are some of the advantages of each platform that we can combine into a solution that doesn't have to compromise. Some of the advantages of the Raspberry Pi. Processing power. The Raspberry Pi has a lot more processing power than the Arduino, so it can do much more. This includes multitasking, allowing it to handle multiple different things at the same time. Wi-Fi. Wireless networking is included as standard on many of the Raspberry Pi models. It is now included on some of the Arduinos, although these tend to be the more expensive models. A USB controller. One of the things I'm looking to use is a USB games controller, which will work with the USB on the Raspberry Pi, but is not available for the Arduino. There is the option to use a camera on the Raspberry Pi. This could be used for showing images to the user, but could also be used with the processing power of certain Raspberry Pi models for facial recognition or some other analysis of the surroundings. You can also run a full web server on the Raspberry Pi, so that can include fully interactive standalone web functionality. Finally, audio support is better on the Raspberry Pi than can be provided by the Arduino. If you want realistic sounds or voice, then that would be very difficult to achieve with the Arduino, whereas it can be as simple as adding a speaker for the Raspberry Pi. Now, looking at the Arduino, it benefits from real-time features such as accurate signal timing and real-time response. This depends upon the needs, but when communicating using certain protocols can be more reliable. It's sometimes possible to do this with the Raspberry Pi as well. For example, the NeoPixel code for the Raspberry Pi managed to create the signals required for the NeoPixels, but this is not as easy to achieve as on the Arduino. The 5-volt output voltage of some models of Arduino can be an advantage. A good example is for driving servos that need a 5-volt signal, and again, NeoPixels. You can change the voltages using a level shifter, but in this case it's another advantage of the Arduino. The analog inputs can be an advantage if you have analog sensors. To do the same on a Raspberry Pi either involves creating an RC timing circuit and calculating time taken to charge a capacitor, or an external analog to digital converter. Another advantage is where a specific hardware has Arduino libraries available. You may be able to work out what is required and rewrite that for the Raspberry Pi, but when it's already available for the Arduino, then that's another advantage. Finally, to say that using these together means that you can share the load, using the best parts of each. So the Arduino can handle the timing of signals to the various outputs without putting any load on the Raspberry Pi, and the Raspberry Pi can handle communication from a network interface without putting any of that on the Arduino. There is a little overhead because of the communication between the Raspberry Pi and the Arduino, but it's going to be very small compared to trying to run the equivalent on just one platform. This is the setup I've got here, which is just to demonstrate the Raspberry Pi and Arduino communications. There is an Arduino, which has an analog input. In this case, I'm using variable resistor. This could be any kind of analog input, such as a light sensor using a light-dependent resistor. There is then a digital output, which in this case just lights up a blue LED. Again, this is just a simple demonstration, so you could use these to drive servo motors, control hundreds of NeoPixels, or just about any other kind of electronics. In this case, I've connected the Arduino to one of the USB ports on the Raspberry Pi. This is plug and play. You just connect the cable and the Raspberry Pi will detect it as a serial device, and then you can communicate with it. An alternative is that both the Arduino and Raspberry Pi have pins which can be used for direct serial communications. These involve a lot more setup. You may need to use a level shifter between the two due to voltage differences, which could otherwise damage the Raspberry Pi. This could be as simple as a resistor voltage divider, although when I tried that it was quite prone to noise. You may then need to enable the mini UART, which is used on some models of the Raspberry Pi. There are also different serial ports on the Arduino depending upon which model you are using, so you may need different code depending upon the Arduino model. I may cover this in a future video, but for this video I'm just concentrating on the software side of communicating between two serial devices, and it's easier to stick with the USB port. I'll put some links in the description to the Raspberry Pi and Arduino serial pages, which you may need to refer to if you want to use the pins such as the GPIO on the Raspberry Pi. You may notice that this is a Raspberry Pi 4 that I'm using here. My end solution would be battery powered, so it most likely be based around a Raspberry Pi Zero, or at least an older model of the Raspberry Pi compared to the 4. However, the Arduino IDE can only be run on newer processors, or at least if you want to use the version that is in the default repositories for the Raspberry Pi OS. So for the initial setup, you should be looking at using a Raspberry Pi 3 or 4. Alternatively, you can use a different computer while setting up the Arduino and then connect it to the Raspberry Pi once that's set up. The IDE is available for Linux, Windows or Mac, so you can use a variety of other computers to program the Arduino if you prefer. From a circuit point of view, there is just the one potentiometer. It's a 10 kilo ohm variable resistor which connects from the plus 5 volts to ground with the centre point connected to the analog input A0. There is then a blue LED which is connected through a 330 ohm resistor to digital pin 2 and then to ground at the other end. I haven't used digital pins 0 or 1 as those are the serial pins on the Arduino, so I'll leave those for future use if I switch to direct connection. Also, for certain Arduino boards, connecting to those can prevent reliable uploads through the USB port, so they're best avoided anyway. If you have one of the more powerful Raspberry Pis, then you can install the Arduino IDE directly using sudo apt install Arduino. Otherwise, you can install an appropriate IDE from the Arduino website, perhaps for a Windows laptop, etc. You only need the IDE for the program code for the Arduino. Once you've uploaded the code, then you can switch to any Raspberry Pi instead. Once installed, you'll find the Arduino IDE on the programming menu. The Arduino IDE includes some sample code for serial communications. The code provided here is used to send a single byte back and forth, but it's quite limiting. It's okay if you're looking at the status of a single pin, say, and you could expand it so it could pass a series of codes back and forth. But instead, I wanted to use text instructions with appropriate responses. Whilst not as efficient, it's useful when trying to debug as it means you can do some testing through the serial monitor, which I'll explain later in this video. There's also some more example code called serial event. This uses the serial event function to capture serial data received. The code I add is going to be similar to this, but I've created my own protocol for the messaging instead. So it's a little bit different from the one here. First, I'm going to start with the basic code to handle the digital output and the analog input. This is very basic Arduino code, so I'll run through it quite quickly, then I'll add the serial communications afterwards. Defines the analog pin as being A0 and the output pin, which is a digital output, as pin 2. Has a variable called input value where the analog input can be stored. And then as part of the setup, it sets the digital output as an output and sets the value high so it turns the LED on initially. I've created a loop, but at the moment there's just a delay in it, so it's not actually doing anything. So if you try and run this code, it's not going to do anything other than turn the LED on. First, I'll add the code which allows the serial port on the Arduino to send messages to the Raspberry Pi. Then I'll add the code that works in the opposite direction. One of the things that I'm doing here is to make sure all the messages that are sent are in human readable form. It doesn't need this if it's just communicating with a computer, and would make for more compact messages if this was sent as binary data. It's going to be much easier to understand and will help us to test using a serial console before we move on to using the Raspberry Pi to send the messages to the Arduino. The first thing I'm going to add is into the setup loop, the setup function, I'm going to add the serial connection. On the Arduino, serial refers to the USB port. It can sometimes refer to the pins on the Arduino as well, but that depends on the model, as I mentioned earlier. So serial.begin is going to enable the serial port and allow me to give it a value for the baud rate. I'm just going to choose 9,600 bits per second, which is a very slow speed, but we don't need any faster than that, and the slow speed will work better for reliability. Then just going to wait until the serial port is ready to connect. This is needed for Leonardo boards in particular, which is actually the one I'm using, but there's no harm in it being in place for other Arduinos, so it's fine. Now in the loop I'm going to add the code that sends the status of the variable resistor, the potentiometer, or the analog input, whatever you want to call it, into and pass that over the serial port. Rather than putting it all in the loop, I'm just going to create a function to put it in. I'm going to call the function send status. So that's what it's going to get called there. Probably send it a little bit more frequently than that. And then add that function. So I'm just going to create a text buffer here. So it's a character string. So I should say 50. That gives it 50 characters to store. Going to get an input value from the analog port. As you can see, this is using the same variable I created up here, so it's just I'd already created that to store it in. And use the analog read, and then I'm going to convert this into a string using sprintf. So printf is the print function often used in C and C++. Sprintf does the same, but instead of printing to the screen or the console, it prints into a character string, and I'm going to save it inside this buffer string. So what it's going to do is print the output into this buffer. So that's where I specify the buffer it's going to save it in, and then it uses a format for this, which is the printf format, which you can find easy enough, and %d means a decimal value. So I'm going to say the analog input, and then I'm going to give the analog pin number, and note it's A0 here, but it's actually got an internal reference number, so it'll print that instead, but it doesn't really matter for this purpose. And then the second variable is going to be the value of that. So I'm going to put the analog pin, input value, and then to send this out on the serial port, I'm going to use the serial.println function. You could just use just print without the ln on the end, but that wouldn't include the carriage return. So whichever you prefer, but in this case I'm going to terminate it with a carriage return so that we know what's been sent. And that's the code for this first part. So it's quite straightforward. We make sure the terminal port's being found. That one is, I've actually got the it connected via the pins as well at the moment, but so due to reliability I'm going to just stick with this one at the moment. And the board is the Leonardo board. So it's going to compile a sketch and then upload it. When it says done uploading, not before, then you can go to Tools and Serial Monitor, and we can see that it's outputting the values. So this is going past really quickly. Analog input 18 says the A0 pin, and then that's the value of the variable resistor. So now we've got the Arduino that's able to send messages to us, but it's not able to receive any messages. So that's the next part of the code that I'm going to add now. So first I'm going to start with a couple of new variables. A string. Now in C and C++, there's two ways of having a string. One is a string of characters, as in the buffer that we created earlier, which was effectively an array of the individual characters, which is traditional C, or there's this new string object that was added more recently. And this one is going to need this string object because it's manipulated in a different way. And then a Boolean value, which is just going to tell us when we've got a complete string that's been read in. So this is going to store the string that's received on the serial port, and then this will let us know when we've got a complete message on that serial port. Within, I'm going to change this send status that's in the loop, and just so that we know that it's sending, I'm going to add it to the setup so that it constantly sends the status until we get a response. So what it's going to do is look for the serial port having some available data on it. Until that happens, then it's going to keep sending some data. So it's going to keep waiting until it sees something that's sent to it. So this is just going to send that status as we had before on here. We'll remove that, and then once we've got some data coming in, then it's going to stop and it's going to start looking at the data. Then inside this loop we're going to say if string complete. So if we've got a complete string, then we're going to handle it. And then this is where I'm creating this sort of protocol myself, that I'm going to look for certain words. So if the input string, which holds our string that we've received, starts with status, so it doesn't matter what follows it, as long as it starts with the word status, then we'll send the status. Otherwise, if it starts with set, then the set command is going to be used to set the digital pin either on or off, turning the LED on or off. And we're going to look for the word on. Now, this isn't going to rather than looking at the string character by character, what I'm doing is it's a bit of a shortcut. I'm just going to quickly check, does the word on appear in this string? If it does, then we're saying we've got set on. If it's got off, then it's got set off. If you were having multiple devices that you wanted to turn on and off, then you'd probably want to be a bit more accurate about the string, but this is sufficient for what we're doing here. And so if we're told to turn it on, we will turn it on, just using the normal Arduino pin, digital write string, and then we'll send a message to say that we turn the LED on. Otherwise, if we see the word off, then we'll see that as an instruction to turn the LED off or turn it low. And again, we'll send a message to say what its status is. And if we don't get either the word on or off, then we'll give an error. And back here, we're now alongside this, so we've got status set and we don't have any others, so we'll put else. We'll give another error message here. So if we get a set command that's not valid, then it sets an invalid set command. And if we get a command that we don't recognize at all, we'll just call it invalid command. Whatever happens here, as long as we're in this if string complete, then we have to reset the string ready for the next one. So I'll just set the string complete to false and get rid of the data inside the string. The IDE sort of pushed me along a bit, so I'm getting the feeling I might have missed a brace. Just do a quick check here. So I think there should have been a closing brace there, that's it. And that closes that. I just realised this should have been else if as well. So that's better. So this won't actually work at the moment though, because there's nothing collecting the data and storing it in here. So let's go work on next. So to do that, I'm going to add, pop it at the bottom, a new function called send event. Sorry, serial event. This will be called after each loop and whenever there's any serial data, so it can handle that. But there is a slight catch for this. I'll mention that in a second. So if there's any data available on the serial port, which is what this line is doing, we get the character cast it as a character because it will be a byte. And then add it to that input string that we mentioned earlier. And this is one of the things you can do with it being a string format. You can just append it to it by using plus equals rather than having to add it to the end of an array and move your null terminator. Now, if the input character is a /n, which is a new line, then we'll treat that as being the end of the string and set string complete to true. Okay, and for most Arduinos that's the code. So the slight gotcha I mentioned is that the serial event doesn't work or doesn't get called on the Arduino, on the Leonardo Arduino. I'm not sure exactly why that is. I think it may be due to being able to use the Leonardo as though it's a virtual keyboard, and therefore it's it could interrupt with that functionality if you're using that, but that's just speculation on my behalf. But basically there's a fairly straightforward workaround in just adding a extra step at the bottom of the loop to call it manually. So only call it if there's something available on the serial port. So you don't need to do that unless you're using a Leonardo, but there's no harm in putting it. It'll still work on other Arduinos even if that's there. So now we can give it a test. So I'll compile and push that to the Arduino. And once it's done uploading, we can start the serial monitor. And as you can see, it's given the same as before. Now this serial monitor sends it all as one line, and you need to make sure the new line option is on there as well, otherwise it won't send the new line. So we can send the status command, and what it's done, it would have stopped at this line here from the setup loop, and then this would be the response from the status. And I can set the LED on and set the LED off, and I can ask for the status, and if I give it any other command, it just says invalid command. And there we go. So now we've got the Arduino, the Raspberry Pi able to talk to each other just using this serial console. So that's the Arduino bit done, and it's time to move on to the Raspberry Pi. So on the code that's going to run on the Raspberry Pi, there is some examples in those other examples I showed you, but that was in processing language. I'm going to use Python. I think Python's quite an easy to use language, and it's the one I often turn to. I'm going to use the Mu editor. If you've not got this installed, it's only installed as part of the full install, not the basic install. Then it's just the sudo apt install mu-editor. That's mu, but it's already installed here, so I'm just going to launch that. And I've already got the code in here, so rather than typing it out, I'll just go through it and explain what's happening and how it works. So the hashbang line, just to say, runs Python 3. We need the serial module and the time module. Create a serial object called ser, S-E-R, based on the serial module and serial. So this is the device port on the Raspberry Pi that refers to the USB device that's been connected. On the Arduino IDE, that is this one here. And it can be different for some other Arduino boards, and it can also be different for the same board. If it loses a connection and then reconnects, it can sometimes end up with ACM1 instead. And if using some different boards, then this might be TTY USB 0 or something like that. So that's something you might need to check for your own code. the baud rate 9600 to agree with the Arduino. And now it's very important you include a timeout here, because if not, then it can get stuck in a loop forever waiting for a response from the Arduino if the Arduino is not sending a response. So important to include a timeout, and that's set at 5 seconds. And that just means that if you did issue a read command, it doesn't get a response within 5 seconds, it'll just return a blank string. So the first line, I've just used a read line to read the first input. So the first input I'm going to just read and echo it straight back to the screen. And this is the string that's received, and it needs to be decoded just to convert it to the right character set, and just use UTF-8, which is a basic ASCII character set, and strip will remove any trailing carriage returns. That way we've got control over them, we can put those in wherever we want them. And then after that, then the rest of this is contained in a while loop, and it just writes a byte string asking for the status with the new line. Remember, the new line's needed for the Arduino, and then it reads whatever comes back. And it's got 5 seconds, it'll wait. If it doesn't receive anything in 5 seconds, then it just moves, it will return an empty string. So in that case, I just print dot to indicate we're waiting. Otherwise, it will print back the response that we get. And sleep for 5 seconds. And then it's going to set the LED to on. And it's going to display the same response we receive, and then it's going to set it to off, and then it's going to go back around the loop again. So straight after the set off, it's going to, there's no sleep there, it'll go straight to asking for the status. So literally click play, run, right. And as you can see, the first one didn't come anything back. That's because we'd actually stopped that running when we were using the console, and that's why it was quite important that it's got this timeout. So that did timeout for 5 seconds, and now as you can see, it's setting those analog, turning the LEDs off, on and off, and we can stop that. We can just restart that again. You could just press the button, the reset button on the Arduino as well, but that just re-pushes the code. And if we click run it again, see, the first time it came back straight away because the Arduino was already outputting these messages as a regular interval. And so that's our code. So this is the code in Python running on the Raspberry Pi. This is the code in C++ running on the Arduino. You don't need this anymore because the Arduino, once you've uploaded the code to the Arduino, it'll stay on there until you overwrite it. And whenever you plug the Arduino in, it'll start running and just start sending the messages and listening for messages to coming back. So now at the end of that, we've got an Arduino and Raspberry Pi talking to each other. So the next thing would be to incorporate this into whatever functionality you wanted to add on both the Raspberry Pi and the Arduino. I've got some projects in mind for this which I'm working on. They're a bit more involved, so it may take me a while before I can add a video on those. But if you'd like to know when I do, then click on the subscribe and bell icons so that you get notified when they're available. Thanks for watching. If you found this useful, please give it a thumbs up and share, and leave a comment if you have any suggestions for other topics you'd like me to cover.